This is problem 30 from section 15.3 on conservative vector fields. We're given this potential function x plus y plus z and a curve r of t given by sine t, cosine t, and t divided by pi as t ranges from 0 to pi. In this problem we're going to evaluate the integral over the curve of the gradient field for phi dot dr in two ways. We're going to use this parametric description of the curve and evaluate this integral directly, and the second method is going to be using the fundamental theorem for line integrals. So first of all, let's compute the gradient, taking partial derivatives of this function. With respect to x, we get 1. With respect partial derivative with respect to y, we get 1 as well. And finally, this partial derivative with respect to z is just 1. And now this dr, remember that that's r prime of t dt. So taking the velocity of our curve, we obtain cosine t, negative sine t, and 1 over pi. So now using this parameterization, the integral becomes the integral from 0 to pi of the dot product of this 1, 1, 1 vector with r prime cosine negative sine 1 over pi. So that becomes cosine t minus sine t plus 1 over pi. And we're going to integrate this from 0 to pi. Now taking antiderivatives, we end up with sine t plus cosine t plus 1 over pi times t. And this will be evaluated from 0 to pi. So sine of pi is 0 plus negative 1 plus pi over pi is positive 1. Now when we evaluate this expression at 0, we get minus 0 plus 1 plus 0. And then we get 0 minus 1 as our answer. Now in part B, we're asked to find the integral a second way, and now we're going to find it by using the fundamental theorem of line integrals. So the fundamental theorem of line integrals says, rather than evaluate the gradient field along this curve, we can evaluate the potential function at the endpoints of the curve. So we're just going to plug 0 and pi into this curve, and then plug those 2 points into phi. So this is going to be phi of r of pi minus phi at r of 0. And this is phi of, well, when we plug in pi, we get sine of pi, that's 0. Cosine of pi is negative 1. And pi over pi is 1. And then we're going to subtract phi at r of 0. So then r of 0 is 0, positive 1, 0. And now plugging in these numbers for phi, remember phi is x plus y plus z, so we get 0 plus minus 1 plus 1, that is 0 minus 1, and again we get negative 1, which is what we obtained doing it the other way. So we have verified the fundamental theorem of line integrals for this particular potential function and curve.